Friends, today we shall learn reflexive relation, symmetric relation, transitive relation and antisymmetric relation. First of all, we shall start with reflexive relation. Please see the full video and get the total concept. Subscribe the channel and never miss any update. Share the video link to your friends to help them. Okay friends, what is reflexive relation? A relation R on a set A is said to be a reflexive relation if every element of A, set A, is related to itself. That is, R is reflexive if A, belongs to R for all A belongs to the set A. Again I repeat, a relation R on a set A is said to be reflexive if every element of A is related to itself. That is, R is reflexive if and only if A, belongs to R for all A belongs to the set A. That is, A is related to itself. A, R, A. Now one example we want to show here. Suppose we consider a set capital A which contains three elements 1, 2 and 3. Okay, then we consider a relation say R like this. Ordered pairs 1, 1, 2, 2, 3, 3, 2, 1. Okay, this relation is reflexive. This relation is reflexive on the set A. But why this relation is reflexive on this set A? Because we see that 1 is an element of the set A and 1 is related to 1. Here 2 is an element of the set A and 2 is related to 2. 3 is an element of set A and 3 is related to 3. For this relation is symmetric relation. This is reflexive relation. Now we consider another relation say R1 which contains say 1, 1, 3, 3, 2, 1, say 3, 2 like this. So in this relation we do not find 2, 2 because 2, 2 does not belong to R1. So this is not a reflexive relation. R1 is not reflexive. R1 is not reflexive. In the first example, R is reflexive relation, but R1 is not reflexive on the set A. Let L be the set of all lines in a plane. Okay, then the relation R on L defined by L1, L2 belongs to R if and only if L1 is parallel to L2 is reflexive. We consider a plane, say this is the plane P. Okay, in this plane there are several lines. So this is L1, this one is L2 say, this one is L3 say, like this. If we take this line, only this line L1, so we can say that L1 is parallel to L1. We can say L2 is parallel to L2. Even we can say L3 is parallel to L3, because we know that each and every line is parallel to itself. So the relation parallel to is a reflexive relation under these set of lines. Okay. Symmetric relation. A relation R on a set A is said to be a symmetric relation if and only if A, B belongs to R. Implies that B, A belongs to R for all A, B belongs to the set A. That is, we can say that ARB implies BRA. That is, A is related to B. It implies that B is related to A for all A, B belongs to the set A. Let L be the set of all lines in a plane. So this is a plane, and capital L be the set of all lines in this plane. Okay, so let us consider the RB a relation defined on L by the rule like this: x, y belongs to R implies that x is perpendicular on y. Then R is symmetric relation. See that suppose we draw a line, say this is L1, okay, this is the line L1, and there is another line, say L2, okay, L2. So this L1 is parallel to L2. If it is given that L1 is parallel to L2, then obviously L2 is also parallel to L1, isn't it? If L1 is parallel to L2, then obviously L2 is also parallel to L1. So we can say that L1, L2 belongs to R. It implies that L2, L1 also belongs to R. Okay. So now we shall take a numerical example. Let us consider that A be a set which contains some elements, say 1, 2, 3, 4. Okay, and R1 and R2 be two relations on set A, given by, say, R1 is equal to ordered pair 1, 3, 1, 4, 3, 1, 2, 2, 4, 1, and another example we take, say relation R2 is equal to 1, 1, 2, 2, 3, 3, 1, 3. Okay, from this it is clear that R1 is symmetric relation. Why? R1 is symmetric relation on A. However, R2 is not, because you see that 1, 3 belongs to R1. Okay, 1, 3 belongs to R1, and 3, 1 is also belonging to R1. So this is correct. Next we take 1, 4 is belonging to R1, and 4, 1 also belongs to R1. 2, 2 belongs to R1, and on the other hand its opposite 2, 2 also belongs to R1. For this is an example of symmetric relation. But here we see that 1, 3 belongs to R1, R2. 1, 3 belongs to R2, but it does not imply that 3, 1 also belongs to R2. This does not imply 3, 1 belongs to R2. For this, R2 is not symmetric. This is not symmetric, but R1 is symmetric. Okay. Next we shall study on transitive relations. Transitive relation. Let capital A be any set. A relation R on A is said to be a transitive relation if and only if A, B belongs to R, ordered pair AB belongs to R, and ordered pair B, C belongs to R, implies that A, C, ordered pair AC belongs to R for all A, B, C belongs to A. That is, A is related to B and B is related to C implies that A is related to C. For all A, B, C belongs to A. Okay? So friends, we have to illustrate this one. The relation R on the set N of all natural numbers defined by, say, xy belongs to R if and only if x divides y. Okay, for all xy belongs to n. Xy belong to n. This is transitive. Okay, this is transitive. We shall show this one. Let us consider that x, y, z belong to n. Besides that, xy belong to xy, ordered pair xy belongs to R, and ordered pair yz belongs to R. Then what can we write? We can write from here that x divides y and yz belongs to R means y divides z. Okay, so can we write x divides y as x is equal, y is equal to, say, m into x. X divides y, so y can be written as m times of x. M is a scalar quantity, and since y divides z, so we can write z is equal to n into say y. Z is equal to n into y. So from these two we can write z is equal to, this is z is equal to ny. So y is equal to mx. So we can write z is equal to n into y. In place of y we write mx. Okay, this is mx. So that means z is equal to m into n times of x. It implies that x divides y, sorry, z, x divides z. It implies that x comma z, that is the ordered pair, belongs to R. So what we considered earlier? We considered xy belongs to R and yz belongs to R. Now we found that xz belongs to R. That is, x is related to y and y is related to z. Now we find that x is related to z. For this relation R is transitive relation on n. So now we shall find what is antisymmetric relation. Now antisymmetric relation. Let A be any set. A relation R on a set A is said to be antisymmetric relation if and only if the ordered pair AB belongs to R and the ordered pair BA belongs to R. These two combined implies that A is equal to B. A is equal to B for all A, B belongs to the set A. Okay, A is related to B and B is related to A. It implies that A is equal to B. They are equal to each other. A is equal to B. Now we want to illustrate this one. Friends, let R be a relation on set N of natural numbers defined by, say, x, r, y. X divides y. Okay, the relation is given divides x and divides y. So x and y belonging to the set N, the set of natural numbers. This relation is an anti-symmetric relation on N, since for any two numbers, say AB belongs to N, A divides B, this is the notation of divides, A divides B and B divides A, so it obviously implies that A is equal to B. You may take an example, say 5 divides 5, and on the other hand, if you revise this, 5 divides 5, so obviously it implies that 5 is equal to 5. So in arbitrary notation, A divides B, and if it is given that B also divides A, then it implies that A is equal to B. A is equal to B. That is, A is related to B and B is related to A. It implies that A is equal to B. Okay, it should be noted that this relation is not antisymmetric on the set Z of integers, because we find that for any non-zero integers A, say A are minus A and minus A are A, but you can't say A is equal to minus A. That is, A is not is equal to minus A. Thank you. Have a nice day.